The cosmos never ceases to amaze us. With every new observation, our understanding expands. The James Webb Space Telescope, or JWST, is at the forefront of this exploration. It peers into the distant universe with unparalleled clarity. Recently, this powerful observatory has delivered another stunning revelation. Astronomers using JWST have made a groundbreaking discovery. They have found a specific molecule in the atmosphere of a faraway exoplanet. This planet is known as WASP 121b. This finding marks a significant step forward in our quest to understand worlds beyond our own solar system. It opens new windows into planetary science. WASP 121b is not just any exoplanet, it belongs to a category known as ultra-hot Jupiters. These are gas giants, similar in nature to Jupiter in our solar system. However, they orbit incredibly close to their parent stars. This proximity makes them intensely hot, unlike anything we see locally. WASP 121b orbits an F6-type star. This star is located approximately 881 light-years away from Earth. You can find it in the constellation Puppis, a patch of sky in the southern celestial hemisphere. Imagine traveling for 881 years at the speed of light to reach this fascinating system. That is the vast distance we are talking about. Let us consider the sheer scale of WASP 121b. This exoplanet is a true giant. It is about 1.87 times larger than our own Jupiter in terms of diameter. Think about that for a moment. Jupiter itself is enormous, more than 11 times the diameter of Earth, so WASP 121b is truly colossal. In terms of mass, it is also a heavyweight. It tips the scales at about 1.18 times the mass of Jupiter. This combination of large size and significant mass contributes to its gravitational influence. It also affects the behavior of its extensive atmosphere, which is now under scrutiny. The orbit of WASP 121b is another extreme characteristic. This ultra-hot Jupiter circles its host star in a breathtakingly short period. It completes one full orbit in merely 1.3 Earth days. Compare that to Earth's 365-day year, or even Jupiter's nearly 12-year orbit. This rapid journey means it is incredibly close to its star. Such proximity has profound consequences for the planet. It is tidally locked, meaning one side perpetually faces the star. This results in a permanent day side and a permanent night side. Each experiences vastly different conditions, as we shall see. The star's immense radiation constantly bombards the planet. The day side of WASP 121b is an inferno beyond easy comprehension. Temperatures on this star-facing hemisphere soar to unimaginable levels. Scientists estimate that the day-side temperature exceeds a staggering 3,000 degrees Celsius. To put this into perspective, that is hotter than the melting point of many rocks and metals on Earth. It is even hotter than the surface of some cooler stars. At such extreme temperatures, the atmospheric chemistry becomes very exotic. Materials that we normally consider solid can exist there as gases. The sheer energy input from the nearby star drives this incredible heat. On the other side of WASP 121b, the permanent night side, conditions are somewhat different. While cooler is a relative term here, the night side experiences temperatures around 1,500 degrees Celsius. This is still incredibly hot by any earthly standard. For instance, it is far hotter than the surface of Venus, the hottest planet in our solar system. This temperature is sufficient to melt iron. The difference between the day side and night side is therefore immense. A temperature gradient of about 1,500 degrees Celsius separates the two hemispheres. This creates a dynamic and extreme atmospheric environment unlike any other. This vast temperature difference between the day side and night side is a key feature of WASP 121b. The planet is tidally locked due to its tight orbit. One side is constantly bathed in the intense radiation of its F6-type star. The other side faces the cold, dark expanse of space, never seeing direct starlight. This extreme thermal gradient drives powerful winds. These winds likely whip across the planet at incredible speeds. They attempt to redistribute the immense heat from the day side to the night side. Understanding this energy transport is crucial for comprehending the planet's overall atmospheric behavior. Dr. Thomas Evans Soma from the University of Newcastle provides insight into this phenomenon. He explains that these incredibly high dayside temperatures play a crucial role. They allow compounds that are typically solid on cooler planets to exist as gaseous components. Think about materials like rocks or metals. On Earth, they are solid. On the day side of WASP 121b, they can vaporize and become part of the atmosphere. This unique condition is precisely why astronomers were able to make their recent exciting discovery. The extreme heat unlocks a different kind of chemistry, revealing molecules we might not otherwise expect to find in a gaseous state. The truly big news, published on June 3, 2025 in the journal, is the detection of silicon monoxide. Scientists using the James Webb Space Telescope have conclusively identified silicon monoxide, or SiO, in WASP 121b's atmosphere. This is not just another molecule, it is the first time this particular molecule has been definitively found in any planetary atmosphere beyond our own. This makes the discovery exceptionally significant. It pushes the boundaries of our knowledge about exoplanetary atmospheres. It highlights the remarkable capabilities of the JWST to probe these distant worlds in detail. What exactly is silicon monoxide? Silicon and oxygen are very common elements in the universe. On Earth, they combine to form silicon dioxide, the primary component of sand and quartz. Silicon monoxide, SiO, is a different, simpler molecule consisting of one silicon atom and one oxygen atom. Under normal terrestrial conditions or on cooler planets, SiO would typically be found in solid form, as part of rocky materials. However, on the scorching day side of WASP 121b, with temperatures exceeding 3,000 degrees Celsius, silicon monoxide can exist as a gas. This allows it to be detected within the planet's atmospheric spectrum. Dr. Angeli Piet, from the University of Birmingham, emphasized the importance of this finding. She described the detection of silicon monoxide as genuinely groundbreaking. Identifying SiO provides a crucial window into the chemistry of ultra-hot Jupiters. These extreme environments test our understanding of how molecules behave under intense heat and radiation. The presence of gaseous SiO confirms that the conditions on WASP 121b's day side are indeed hot enough to vaporize rocky materials. This directly supports the temperature models for such planets. It also gives us a new tracer molecule to study these fascinating worlds. The importance of detecting silicon monoxide extends further. It helps astronomers build a more complete picture of the atmospheric composition of ultra-hot Jupiters. By identifying the various chemical species present, scientists can refine their models of planetary atmospheres. This can provide clues about how these planets formed and how they have evolved over time. Are the elements present in the ratios we expect? Does the presence of SiO tell us anything about the planet's core, or perhaps about material being stripped from the planet by its star? These are the questions that such discoveries help us to begin answering with more confidence. Silicon monoxide was not the only molecule found hanging out in WASP 121b's fiery atmosphere. The JWST data also revealed the presence of other familiar molecules on the planet's day side. These include water vapor, H2O, and carbon monoxide, CO. While water and carbon monoxide are commonly detected in the atmospheres of hot Jupiters, their coexistence with silicon monoxide provides a richer chemical inventory. Understanding how these different molecules interact under such extreme conditions is a key area of ongoing research. Each detection adds another piece to the complex puzzle of exoplanet atmospheric chemistry. Perhaps more surprisingly, the observations of WASP 121b's cooler night side yielded an unexpected detection. Methane, CH4. Methane is a molecule that is typically not expected to be stable at the still very high temperatures found even on the night side of an ultra-hot Jupiter, around 1,500 degrees Celsius. Its presence there is quite puzzling. This suggests that the planet's atmosphere is not static or simple. There must be dynamic processes at play. These processes are likely transporting methane from other, perhaps deeper and cooler regions of the atmosphere to the observable night side before it can be destroyed. The presence of methane on the night side points towards complex atmospheric circulation. Scientists theorize that strong vertical mixing could be responsible. This means that gas is being dredged up from deeper, potentially cooler layers of the planet's atmosphere. In these deeper layers, methane might be more stable or be actively produced. This material is then transported upwards and horizontally by strong winds to the night side. This finding highlights the three-dimensional nature of exoplanet atmospheres. They are not simple, uniform layers but dynamic systems with complex weather patterns and chemical transport. To achieve these remarkable insights, researchers employed a technique called phase curve observation. This involves meticulously tracking the changes in the planet's overall brightness as it orbits its star. As WASP 121b goes through its phases, similar to the Moon's phases, different parts of its atmosphere are presented to the telescope. By analyzing the subtle variations in infrared light emitted by the planet at different points in its orbit, scientists can create a map. This map reveals the chemical composition and temperature differences between the day side, the night side, and the terminator region, the boundary between them. This powerful technique, enhanced by JWST's sensitivity, promises many more exoplanet revelations.